Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to be talking about wood mechanics and modification factors. So starting just from a basis of overall density and stiffness and strength of wood compared to other materials, it's clear that wood in general, if I just took like a similar sized piece of wood to a similar size of steel or aluminum or concrete, that wood is both weaker and less stiff, as indicated by the Young's modulus, and also less dense, so lighter. So of course, the only thing that it's stronger than is concrete in tension, but we all know that concrete has very low tensile strength. So, the question arises, like, why would we ever use wood at all if it's not efficient? Well, the reason is because if we look at it from a point of view of strength versus weight, then wood suddenly becomes very competitive because it has very high strength to weight ratios. For example, if we look at tensile strength as a function of density, like tensile strength divided by density, then you can see that it has strengths that are, much higher than steel and close to that of aluminum per unit weight. And same for compressive strength. It's much stronger than steel or concrete as a function of its density. So it has a very high strength to weight ratio. So that means that when we want to build things out of wood, then the members are going to be very light. They're probably going to be bigger than the comparative mild steel or concrete members, but they may be easier to install and to ship to site and to handle on site. On top of all the other benefits of wood that we talked about in previous videos. Now, if we drill down into the mechanics of wood as a material, and I have my piece of wood over here, we talked about a little bit before that wood is not the same in all directions. So unlike steel, if I load it this way, or I load it this way, or I load it this way, it's going to be the same approximately in every direction. But for wood, that's really not the case. Wood is strongest in its longitudinal direction, which means like me pulling or pushing on it like this. And it's very weak in the radial and tangential directions. And we remember from looking at the cross section of the wood that we have radial direction that comes out from the pith, and we have a tangential direction, which is tangential to the growth rings. Okay. Now, in general, we don't know exactly which direction those rings are going to be in any given piece of wood. But the lucky thing is that tangential and radial strengths and stiffnesses are similar to each other. So that means it doesn't really matter from the point for a piece of wood which way the grain goes. I will consider this direction and this direction to basically be identical for design and use a worst case. And I won't be losing a lot by using the worst case strength or stiffness for radial and tangential. So instead of talking about wood in the context of radial and tangential strengths, we really radial and tangential and longitudinal strengths, we only really talk about it in terms of longitudinal versus perpendicular to the grain strength. So parallel to grain strength, which is equivalent to the longitudinal, and perpendicular to grain strength, which is both radial and tangential. So it doesn't matter if we look at it up and down and side to side, or in the radial direction versus the tangential direction. It's basically the same. So in that sense, wood is not truly an orthotropic material, but we consider it to be an orthotropic material, meaning that we can break down its strength into the three perpendicular axes in three different directions. And you can see here that I've given some idea of the Young's modulus, which is an indication of the material stiffness. Longitudinal, the Young's modulus is much, much higher by a factor of 20 than radial and tangential. And shear modulus, which is if I want to shear this piece of wood, so if I wanted to shear it like this, or if I wanted to shear it like this, or if I wanted to shear it like this, all those are there as well. And the ones that are related to the tangential and radial, like tangential radial longitudinal shear plane and tangential longitudinal shear plane, are the ones that have the highest strength. And this radial tangential shear plane, which is basically in this direction or this direction, is called rolling shear, which is very weak for wood. Now, for different species, they obviously have different strengths, and we talked about hardwood and softwood before. And the strength of the wood is typically directly correlated to the density of the wood. So the more actual wood fiber material in this piece of wood, the stronger it's going to be, basically, per unit volume. And that applies to strengths. You can see here the compression strengths in parallel to grain, which is like pushing like this, and perpendicular to grain, which is pushing either like this or like this. The higher the density, the higher the strength. Modulus of rupture the same, and modulus of elasticity, the stiffness is also approximately linearly proportional to the density. You can see the density of common species that we use for construction here on the right, about 0.4 to 0.49. There's not a lot of range. So 0.4 to 0.49 is in here. So you can see that our compressive parallel to grain strength, for example, varies in quite a small range for the species that we're usually talking about. In fact, probably specimen to specimen differences are going to be much larger. Okay, so for different types of species like cedar, spruce, pine, fir, hemlock, and Doug fir, these are all softwood species that are used for construction. You can see the specific gravity above each. You can't really see my red here. Above each bar here, you can see that as the specific gravity increases, the allowable stress, which is just an indication of strength here for now. These slides are a bit old, so they're not talking about load resistance factor design, but the allowable strength increases as a function of density. So the strongest Canadian species that we use is the Douglas fir and larch species, and you see they have quite a bit stronger strength, a bit higher strength than the others, which is going to be reflected in the design guideline. Okay, so why is it that wood is this way? If we go back to the wood cell, so you can see on the right, wood is made up of a whole bunch of these cells all lined up one beside the other, and we saw some pictures of micrographs of what that kind of looks like, all those cells all lined up together, all oriented in the same direction. And so if we do that and we take a whole bunch of these, line them up all in this longitudinal direction, all thousands and thousands of them, then put them all together, bind them with that material lignin, then we get this solid piece of wood. And the strength of the wood is directly correlated with the strength of the fibers. So the fibers are strongest in the vertical direction, and so the wood is also strongest in the vertical direction. So one way to conceptualize this is using straws. So if we see I have just one straw here, and this straw can represent one wood fiber, and this straw is very strong in tension, except for the fact that this is a bendy straw. It's very strong in tension. It's strong in compression up to the point that it buckles, but it is not very strong in the perpendicular direction, right? I can just smush this straw very, very easily. I'm just smushing this thin circular cross section, which is very similar to what the wood fibers look like. And if I were to pull apart as well in this direction, it's not quite as strong. But for the fiber itself, it's not too bad. But once I stack them all up, it's going to be a problem. So if I take a whole bunch of straws and put them together just with some elastic bands, these elastic bands are now representing the function of the lignin, which holds all these fibers together in the real wood structure. Now I have something that's very strong in tension, very strong in compression, as long as those fibers are all held together by the lignin, and very weak in this direction, and also very weak in this direction, because I can pull those fibers apart potentially, depending on the strength of the lignin again. So we're going to go through each of these mechanisms for loading and relate back to this example of the straws. So, but first, why is wood developed to be this way? Why is the strength of wood in the vertical longitudinal direction? So this is the way the tree grows, right? So here's a piece of wood cut out of a log. The log is vertical. The tree is vertical. the pieces that we cut out of it are in the same direction because that's the long direction of the tree. So that's how we get long pieces of wood. So why is it that the tree has those strongest directions in the vertical? Well, that's because that the primary structural load on trees comes typically from wind. And so wind is a lateral load on the tree, which wants to blow it over. Okay. And so in order to resist bending, you know from mechanics that we need to have tension and compressive stresses in the wood, tension on one side and compression on the other. So if I'm pushing this way, right, then I'm going to have tension on the near face and compression on the far face, just like is shown over here. So if the wind is pushing towards the left on this tree, the right side of the tree is going to be in tension, and the right side is going to be in compression. Those are just the bending stresses in the tree. And there is some shear, but not a lot compared to these primary forces here. And, you know, there's no load on the tree that typically smushes it like this. So it doesn't have to be very strong like that. There's no load on the tree that tries to pull its fibers apart. So it doesn't have to be strong like that. So the tree wood mechanism for resisting that load is very efficient, actually. Okay, so now if we go down detailed into compression, I mean, if we have a fiber, if we have a short fiber, it's going to be very strong in compression. It's like, you know, like if we had a steel tube and we put it in compression, it's very strong. Now these fibers, of course, are very, very long in comparison to their width. So if we just had one fiber and we pressed on it and it's very long, it's going to buckle, right, as we can imagine. But if I take a whole bunch of those fibers and put them together and I hold them together with a lignin matrix, this acts as a composite, and now it's very, very strong for compression because each fiber is bracing all of the other fibers next to it to prevent them all from buckling. So in order for this whole assembly to buckle, the entire assembly has to buckle together. So now, since you know buckling is directly related to the second moment of area, or the moment of inertia, the more fibers I add here and the deeper the section, as long as they're held together tight with the lignin, I could have a very high compressive strength to prevent buckling. Compression perpendicular to grain. So I have my piece of wood and I'm pressing it perpendicular to grain now. I mean, if I just have this piece of wood here and I'm holding it in my hands, I mean, it feels very strong. But if I were to load it with a testing machine and I looked at vertical compression like this versus compression perpendicular to grain like this, I would find a very big difference in the strengths. Perpendicular to grain is very weak comparatively because I'm squishing the fibers like this, and squishing a tube like this is very easy to do, especially for thin tubes. And stacking them up doesn't get me that much of a benefit because I still am squishing all the tubes at the surface. So it's still very easy for me to squish this. Okay, so stacking them up and putting them together with lignin doesn't help that much for compression perpendicular to grain. So we obviously have to load wood perpendicular to grain. And we will learn how to do that, but the strength is much less. So we have to pay particular attention to bearing areas. Now let's say that I have compression, but it's not exactly parallel to grain and it's not exactly perpendicular to grain. Then I'm loading it on an angle to the grain. Then I have some component of the load is going parallel, some component of the load is going perpendicular. And I can basically derive an interaction equation to interpolate between those two strengths. And that's exactly what the design standard does. And we'll learn that when we get to compression perpendicular design. Okay, so now tension is very straightforward because I'm just pulling on the fiber. Okay, so the fibers are very strong in tension. So tension strength is quite strong. Putting them all together does not get me a huge benefit because I'm still pulling on the fibers. Now there is something that we mentioned before about wood defects that affects the strength of wood in tension, which is that if I have knots in my piece of wood, and I don't have significant knots in this particular piece, is kind of a clear specimen, I don't have a lot of knots, but if I had a big knot here, then that would reduce the net area available to resist tension, and so that would weaken the tension strength. So although tension in wood is generally very strong, we'll see when we look at the actual values, the compression strengths in the table tend to be a bit higher because they're less affected by the defects. So tension has is affected more by defects in the piece of wood, particularly knots. Okay, now tension perpendicular. I mentioned before, if I try to pull this straw apart, tension perpendicular would be quite strong because I would have to tear the wall of the straw in order to do it. But if I have a whole bunch of straws together and I pull them apart, if I don't have anything holding them together, it's trivial. If I have this lignin holding it together, then of course it's going to depend on the strength of the lignin. And the strength of the lignin is quite a bit less than the strength of the fibers themselves. So the cellulose fibers are quite strong. The lignin comparatively is quite weak. So it's good enough to hold it together to prevent buckling by making all the fibers act as one. But if I try to tear the straws apart from each other just by pulling them, it's quite comparatively easy because the lignin itself is not an extremely strong material. And this is basically the worst way that I can load a piece of wood because the tension perpendicular strength is just that weak. So basically in all of our designs, and we'll talk about this again when we get to connections, but in all of our designs, we always try to avoid loading wood like this. So there's not actually even a strength equation to figure out what this kind of strength is, except for when we calculate connection strength and we talk about splitting. Now, if I have a piece of wood and I'm bending it, the only difference from the others is now I am creating a stress profile across the height of the wood. So I am causing, if I'm bending it downwards, like in this figure, I'm causing compression in the top fibers and tension in the bottom fibers. And compression and tension are good ways to load wood. If I'm talking about parallel to grain, which these are parallel to grain, so I'm compression parallel to grain here, tension parallel to grain here, then the bending strength is actually very good because we're basically relying on these mechanisms that wood is designed for, because trees are they're not designed, but trees are adapted for bending. So wood is also well adapted for bending. So it makes good beams. Okay, the last one that we really need to talk about is shear. So, if we've designed in steel, usually shear is not a big deal. When we design in concrete, shear is a bigger problem. Okay, and when we design in wood, shear actually is also quite a big concern. And that's because when we have bending, we have shear, okay, as we know. So if I'm bending this, I have some shear, and that shear is highest at the center of this rectangular cross section, right? And at that section, basically what's happening is that the fibers are trying to slide against each other, just like shown in this figure at the top. So one set of fibers wants to go one way, the other set of the fibers wants to go the other way. We're shearing it like this, right? So if I bend this, let me go full screen on this so that we can see it a bit better. Okay, if I start to bend this, we'll see that the fibers want to slide against each other when I do this. You can see that when I bend it, the fibers over here, like at the top, want to go out, and at the bottom are trying to go in when I'm doing this, right? So the fibers want to slide against each other, right? So they want to kind of do this when I bend. And what is resisting that movement of the fibers sliding past each other, is again the lignin, which, as we discussed before, is not very strong. So longitudinal shear strength is something that we have to pay close attention to when we're talking about wood design. Okay, so now once we're ready to design, we can go to the handbook. We can use our Canadian Wood Design Manual. And this is the volume 2, which has all of the code clauses and everything in it, and the code commentary. And we can go in here and we can pick out our design strengths from tables. And we're going to learn exactly how to do that in another video. But just to give you some context, here's one, for example, that's for lumber. And you can see we have different species on the left and different grades. And we're going to talk about what those grades mean later in another video. But you can see that for each of these kind of strengths, we have all different strengths. So when we design in steel, we just have one strength, right? Which is our steel yield strength, Fy, which is typically something like 350, or for rebar, you know, it's 400 MPa. But for wood, you see, depending on which kind of failure mode we're talking about, longitudinal shear versus compression parallel to grain versus compression perpendicular to grain, we have all these different strengths. And you can see that bending and compression parallel to grain, and tension parallel to grain are the ones that typically are highest. And you can see that perpendicular to grain compression is lower, and longitudinal shear is the lowest of them all. Okay, and we don't have a tension perpendicular to grain column here because it's even lower still. And so we have to avoid designing for tension perpendicular to grain. On top of the strengths here, it also gives a modulus of elasticity, which is our Young's modulus. And you can see there's two values in the lumber tables. One is E. This E is a mean value. So if they take a whole bunch of tests, we're going to get a value of E on average over all of the tests for this species and this grade, and that's what this value represents. The E05 value is a 5th percentile strength. So if I have a population of different, for example, select structural Douglas fir larch pieces of wood, and I test them all, 95% of them will be stiffer than this. And I use this one versus this one depending on what case I'm designing for. So if I'm trying to figure out deflections, since deflection is a serviceability criteria and it only kind of affects comfort, then I'll use the mean value so that I don't overdo it. But if I'm doing something that affects strength, for example, if I'm designing for compression and I need to make sure that my beam, my column is not buckling, and the buckling strength depends on the stiffness, the Young's modulus, because of, you know, Euler buckling, then I should use this lower value so that I make sure that I don't get buckling. So this is something I definitely don't want to happen, so I use the 5th percentile strength. This is something I just want to keep controlled, so I use the mean. I'll use the mean strength. All these values, by the way, are more like 5th percentile strengths, and we'll talk about we're going to talk about that later in this presentation. For glulam, we have a different table. It's a bit different, and all the glulam values are basically in one table. And but you can see it's the same kind of thing. I have a species and a grade, and then on the left, instead of on the top, now I have all of the different types of design cases that I might want to look at. For example, if I'm interested in designing a piece of glulam for compression perpendicular, then I'm going to get my value out of this row, depending on the species and the grade. Longitudinal shear, again, is very low, and I'm going to take it out of this row. We're going to go through some examples in more detail about how to use these tables to pick out design strengths. Okay, so now unlike steel, there are more things in service, and since wood is a natural material, and since wood is particularly affected by moisture, and because wood is viscoelastic, there are a lot of different modification factors that we have in design. And once you get some experience doing this wood design, you're going to see how these factors just come back again and again and again. It's kind of a tale of factors when we're doing wood design. So we have our resistance factor, which accounts for material strength over a population, which we're going to talk about, that you would probably be familiar with if you've ever looked at steel or concrete design. But all these other ones will be new. Duration of load factor, you know, how long is the load going to be there because wood is viscoelastic. System factor, how many pieces are holding up the same load. This is important because wood has defects. So looking at one piece or looking at multiple pieces is a different story. Service condition is how does moisture affect the wood? You know, what moisture content is the wood going to be at when it's in service? Because we know that adding moisture in wood reduces the strength and the stiffness. Treatment factor is if I've treated the wood, the treatment process weakens the wood a little bit, so we have to account for that. And size factor is another thing that accounts for wood being a natural material, meaning that there could be defects and different natural things that affect the strength of that piece of wood. We're going to talk about these each in turn. So the resistance factor for wood, there are two, depending on which way we're loading it. If we're talking about bending, shear, or tension, then our strength reduction factor for material reliability is 0.9. If we're talking about compression, parallel, and perpendicular, it's 0.8. These numbers are based on reliability analysis. And we do reliability analysis based on a large population of specimens, doing a whole bunch of tests, and seeing what is the distribution of different strengths. This is an example of what that kind of looks like. So if I test a whole bunch of pieces of wood like this, of a specific species and grade, and I test a whole bunch of them, then probably they're not all going to be the same strength, obviously. Their strength is going to be distributed over some range. So if X here is the strength and the vertical axis is the frequency, this distribution is showing how many of, out of all the pieces of wood that I test, how many of them are at this strength, how many of them are at this strength, how many of them are at this strength. And the width of this curve, how wide this is, like if it's very tight and it's just like this, then that would kind of indicate that there's not a lot of variability in the material properties. Like if I had steel, then it might be a little bit thinner. But if I have a natural material like wood, then I'm going to have some that are very low, I'm going to have some that are very high, and there's going to be a whole bunch in between. This particular distribution is a normal distribution. You know, you might have heard it as a Gaussian distribution or a bell curve. This is not actually the distribution that they use for wood. They actually use a Weibull distribution, which limits a bit better what the lower bound values are. But for the purposes of discussion, we're going to talk about everything as if we're talking about normal distribution curves. So if you reach back to statistics and I have this curve, I have a mean value, which is the average value of all of these pieces of wood. If I just take all of the strengths and I divide them by the number, that's what I would get here, mx. Standard deviation is a measure of that spread. So how variable is that population in terms of strength? And I can also look at the area under this curve, which will tell me, you know, what is the chance that a certain number of specimens is below a certain value. So when we're talking about load resistance factor design, LRFD, which is the way that we design structures in Canada, we're talking about two different things, actually. We have the resistances, of course, which is what I just talked about, and those are variable, but the loads, we have to remember, are also not constant. So we have snow load. Snow load is not just one load. I mean, we come up with one load for design, but that load is based on a whole distribution of potential loads that we could get. Okay, so in order to design, of course, we want our resistance to be higher than the load that we're applying. Okay, but we can't really reasonably push this curve so that it's effectively zero here, and this curve so that's effectively zero on the other side. So we're always going to have some kind of overlap because the tails of these curves are quite long. Okay, so we have to make a choice of where we want that overlap to be, and that's where kind of the reliability analysis comes into play. But let's say, for sake of argument, that I want to take the 95th percentile of the load effect. Okay, so that would be such that 95% of all the loads that the structure sees are going to be below that value. So it's like a effective upper bound on the load. And I want to make that less than the 5th percentile of the resistance, so that 95% of all members are going to be stronger than that. Now, is there a chance that I will run into a member that happens to be in the 5th percentile at the same time as I'm getting a load that happens to be above the 95th percentile? So a super rare load and super weak member? Yes, but on the balance, that chance is low. And if we use statistics, we can measure how much that chance is going to be. And it's always going to be non-zero for all of the designs that we do. And that's why when we do structural engineering design, we set a limit and we try to make sure that all the structures we design are about the same level of safety, and that's the reliability. So basically, if I have that resistance and I have that load, and I can calculate basically this safety index by subtracting the population of one from the population of the other, and I end up with this curve on the right, where basically I'm looking at what is the chance that I'm going to get a failure, which means what is the chance that my resistance that I get is going to be less than a load that I get. So if I take all possible pairs of resistances with loads and I add them all up, so I take R minus F, the resistance minus the load, which is basically how much gap do I have between my resistance and my load. As those get closer to and closer together, the subtraction of the two, the Z, the resistance minus the load, is going to get closer and closer to zero. And once I get to zero, that's when my resistance exactly equals my load. And anything less than that means that my member is going to fail under that resistance load combination. So if I do that statistical analysis, then I can integrate underneath this curve to the left of that point 0 where the failure occurs, and I can come up with a probability that my member is going to fail. And basically I want to make sure that that this is the same for all of the structures that I design. And another measure of where that point is basically how many standard deviations is the mean of this Z distribution away from 0. And that is my beta. And beta, another way to think about it is it's the inverse of the coefficient of variation. So if you've done, statistics, the standard deviation divided by the mean is another measure of the variability called the coefficient of variation. If I take the inverse of that, then I get this index B, and this is where I make my stand as far as what is the constant amount of reliability that I want. So we can start with, I want beta to be 2.6. Then I can use a 5 factor to shift this resistance curve either to the left or to the right and redo that until I get a beta that equals 2.6 or greater. And so that's how I determine basically the 5 factor. Again, these are all normal curves. In reality, for wood, it's not a normal curve, but this is a good kind of approximation. Okay, so then we come back and we pick out from that process, what does our phi have to be? And that's where the process typically ends, if we're talking about steel design or concrete design. But for wood, since wood changes depending on the situation it's in, we have a whole bunch of other modification factors we need to talk about. Okay, the first one is our duration of load factor. And I mentioned earlier that this factor is necessary because wood is a viscoelastic material. Another viscoelastic material that you'd be familiar with is concrete. And the way that manifests for concrete is through creep, right? So if I have a load that's applied over a very long time, then I get a very large deformation, okay? In this case, if I look at it instead in terms of strength, if I have a load on wood that's present for a very long time, then my effective strength basically goes down. Okay, so this is load duration in hours. So at about a year and past, my strength reduces. If I load it over a very short period of time, very fast, then the strength is high. And if I use that as a baseline of 100%, then I can figure out, relative to, if I loaded it very fast, like over over an hour, we're not talking about super speed, but, over a short period of time, versus a long period of time, how does the strength of wood change over that time? And we can assign numbers to that. So in this plot, if I start at 100, I go down to about 80 after about 2,000 hours, and I go down to about 65 down here if I'm at a very high number of hours. About 70 if I go to a very high number of hours. Now, in the wood code, they standardize all of the strengths to a certain design case. So what we say basically at 80% of the strength, we set that to 1.0. And then we say if it's loaded shorter than that, then I get an increase of strength relative to that baseline. So then I have basically 100 divided by 80, which gives me 1.15. And if I go very far away, then I get 0.65 relative to that 1. And so why is this important? It's because the loads that we apply to our structure have different durations. So we have dead load on our structure, which is always present. So that load is going to be way out here on the curve. And so those loads will have a lower strength associated with them. Okay, so this is one aspect in which wood is different than designing in steel or concrete. And this is a very different part because basically depending on what load we put on the structure, our strength changes. So the load side affects the resistance side. They're not completely independent. In steel design, I find my resistance is my resistance. I find my load is my load, and I compare them and I just make sure my resistance is greater than my load. But in wood, my resistance actually depends on what kind of load it is. So that's dead loads would be way out here. Live loads, which are things like occupancy loads, people in the building, equipment in the building, stuff like that. Those loads are kind of medium term. So they might be present for a month or 2 months, but not for the entire lifetime of the structure. And that's where we set our baseline of KD equals 1.0. And then short duration loads, loads that happen over hours or days, but not months, actually get a bump in strength according to this baseline. So that would be things like earthquake and wind. There is one caveat here, which is if I have only dead and live load, there is a way to interpolate between these two, KD equals 1.0 and KD equals 0.65. So there's a curve between these two. And if I just have dead and live, I can either just consider it dead, or I can do this interpolation, which gives me a value that will be somewhere in between 1.0 and 0.65 by just basically putting the dead load in here and putting the live load in here, like the actual specified value of the live load, and subbing it into this equation, and I will get a KD that's in between. You see this greater than or equal to 0.65 is because I can't go past, there's no point going past the longest term load. So this equation, if I use certain combination, will come out with something that's less than 0.65, and then I just cap it at that level. You see the letters here are a bit confusing because it has L and S, which do not stand for live and snow or something like that. L here is long term, and S here is standard term. So long term is dead, standard term is snow or live load, and if you have a combination of the two, then it gives some guidance here for how much you should consider for PS. In general, though, if I have other combinations of load, because I have all my load combinations from the NBCC or from the OBC or whatever design code I'm using, I will generally take whichever is the best case scenario for me, which is a bit counterintuitive. Usually you'd say, okay, like I have earthquake load and I have dead load in this load combination. Therefore, the worst case scenario is to just use dead for everything, because dead gives the lowest value of KD, which reduces my strength the maximum amount. But it says explicitly in the design standard that it's the reverse. We should actually take the KD for whichever load is the shortest duration. So if I have a combination between earthquake and dead load, I'll actually use the earthquake KD for the entire load combination when I'm trying to calculate my resistance. So if I'm comparing a resistance to a load combination that includes earthquake and dead, I'm going to use KD 1.15. So it seems unconservative, but the reason is because the chances that you're going to run into the worst case strength for my piece of wood at the same time that I have my worst case earthquake are very low. So it's trying to balance the conservatism that's inherent in this process, which makes it a bit non-intuitive. So just keep that in mind. We'll do examples that show this in some other class activities. Okay, so that's the load duration factor. So that's only one of 5 different important factors that we need to talk about. The second one is our system factor. And this accounts for the fact that if I have multiple pieces of wood supporting the same load, then the risk of having bad defects in those pieces of wood is kind of smoothed out over having multiple ones. So, you know, my design equation for a single piece of wood is going to assume that I have the worst possible defects for that grade. And so I have to take that into account. You know, I'm allowed to have a certain number of knots. Therefore, I'm assuming that I have that number of knots, and I'm designing the piece of wood for that. Now, if I have multiple pieces of wood all supporting the same load, then what are the chances that I'm going to have the worst case layout of knots in every single piece of wood that's supporting that load? It's very low. So in order to balance that over conservatism, we have this system factor, which allows us to increase the resistance if I have multiple pieces of wood supporting the same load. And there are two different cases for this. And the cases are different because they are supporting the load more together, like they're doing a better job of sharing the load or a medium job of sharing the load. So the kind of normal case is the case one system shown here. So I have 3 or more members supporting the same load. So here it's a floor. It could be like 3 studs supporting the same vertical load or something like that. As long as those 3 members are supporting the same load and those members are spaced less than 610 millimeters apart from each other, so they're close enough together that they can support the same load, then I can include this factor KH of 1.1, which means I can increase my load resistance by 10%. So there's the effect of the redundancy caused by, you know, having multiple members. And on top of that, I have potentially the chance for composite action, which is not so great in this example, but is great in this example. So if I have some sheathing connected to those members, like plywood or OSB, and it connects all those members together, then now the sheathing is acting also composite with the beam. So the sheathing is also providing some bending resistance. So I'm allowed to increase my strength a little bit more. And on top of that, the nailing of all of these things together connected by the sheathing makes those members that are supporting the same load more together in supporting that load. So it's more likely that they are supporting that load as kind of one effective member just spread out over a larger space. So for case 2 system factor, I have the same requirements as the first one, 3 or more members sharing the load. They have to be closer than 610 millimeters apart from each other, which is 2 feet. But on top of those requirements, I also have to have sheathing. That sheathing has to be at least 9.5 millimeters thick. I have to have nailing around the edges of the sheathing that's at least 150 millimeters apart, like less than or equal to 150 millimeters apart, and intermediate nailing elsewhere in the sheathing at maximum of 300 millimeters apart. All of these requirements are in the standard, so you'll have read them already if you're following the readings. And there is a table that shows all of these things exactly for the different pieces of wood. So case 1, which is the first one we talked about, you see here, if I'm doing bending, longitudinal shear, compression parallel design, or tension parallel design, then I get to bump up my load by 10%. Other properties, like for example, compression perpendicular design, doesn't get the bump because compression perpendicular design is by definition a local effect. So multiple members can't help to share a bearing load. So we don't get to bump up for that, for example. For case 2, which is the one that we just talked about, for visually graded, you can see that for bending and longitudinal shear, we get a 40% bump. For compression parallel to grain, we don't get that bump because we don't have the composite action happening in that case. And all other properties 0. MSR is machine stress rated lumber, which we're going to talk about, but we won't really have any examples of in this course, but we have different requirements for that. And built up beams is when I have multiple beams all stuck together, and I have a different requirement for that as well. Okay, moving on to number 3, the service condition factor. So this is the factor that accounts for the fact that the properties of wood change when it gets wet and when the moisture content of the wood goes up, as we see here. So moisture content of the wood is going up as we go from left to right. You can see that my strength of crushing goes down, my stiffness goes down. Basically all of the strength values go down. So we have to account for that. So if I have wet wood and I know that in service my wood is going to have a high moisture content, then I need to lower my strength to account for that. I have like a little, slogan here: wetter is weaker. Okay, so what counts for dry and what counts for wet? Well, there is a definition in the standard, and dry basically means, so if you're saying that your wood is dry, so you're going to not consider the effective service condition factor, then the average yearly moisture content has to be less than 15%, and at no time in the year can it go higher than 19%. So it can fluctuate. It can go past 15 for some time as long as the average is less than 15, but it can't go past 19. And these factors are different for lumber and glulam. So there's different tables for lumber and for glulam. This is the lumber one. So you can see that for dry, we basically have our baseline condition, so everything is 1. And for wet, we have different values. So for example, for bending, so it depends on what kind of load we're applying, how moisture affects it. So for bending, we get a 16% reduction if we have a wet condition. If we have shear, we get a 30% reduction. Okay, so it's going to affect for shear more, presumably because it's going to affect the lignin more, the lignin strength more. Compression parallel to grain, we get another big reduction here. Okay. Now we have a different here between sawn lumber, between the size of the member. Okay, so the smaller the member, the more wet the piece of wood is going to be over the cross section, because as we talked about when we talked about moisture content, equilibrium moisture content happens over potentially a long period of time. So if I have a smaller piece of wood like this, then it's easier for the moisture to get all the way to the center. Okay, but if I have a large piece of wood where the least dimension, so here I have a 38 by 89, this is a 2 by 4, the least dimension here is 38. Okay, so 38 is not greater than 89, so I have to do this one. If the least dimension here, so if this was a 4 by 4 or bigger, then some of those are going to be 1, and the rest are going to typically have a higher strength. And that's because the moisture can't as easily impact through the entire section of the wood, because it takes time for the moisture to diffuse from the outside surface to the inside. This is the same for glulam, and glulam does not have that stipulation. You'll find that there are a lot of differences between lumber and glulam that seem like, why don't we treat glulam the same way that we treat lumber? And sometimes the reason for that is just because the research was done by different people and they took a different approach when they went to do the tests, and they came up with different numbers. So although it would be ideal if lumber and glulam were treated the exact same way in every case, there are some differences. But anyway, here for glulam, we have wet versus dry. The wet values you see, though, are higher than the wet values for the small pieces of lumber. And that's because the glulam pieces are generally quite a lot bigger than lumber pieces are. Okay, moving on to I think we're on number 4, right? Modification factor type number 4, which is treatment factor. And this accounts for the fact that sometimes we want to treat wood. So we want to give it a preservative that's either going to prevent rot or prevent fire or something like that. And whether we need to reduce the strength or not depends on, A, kind of what the chemical is, but B, typically how we got the treatment into the piece of wood. So you see here that we have untreated lumber, everything's 1. Preservative treated unincised lumber, we'll talk about what unincised means, is both 1. So no reduction in strength. Preservative treated incised lumber of thickness 89 or less, then we start to have these reductions, and the reduction is higher the reduction is less for wet service condition than dry service condition. And for fire retardant treated, basically it says that you have to go to the manufacturer and figure out from them what your reduction should be. Now, what is incised versus unincised? Well, incised means that basically they cut a bunch of small slots in the piece of wood, the purpose being that it allows the treatment chemical to get into the wood further easier. But the process of cutting those slots affects the strength at the surface, and so it affects a little bit the strength of the entire piece of wood. So if we incise it to treat it, then we have to reduce the strength. Okay. Finishing our marathon on size factor. So this is the last kind of factor that we need to talk about. You see some of them come in this table, some of them are in clauses, like some of them are calculations. So there's a equation for calculating the size factor. But you'll see on the left there, it says, why do we have a size factor? Because large members are weaker. Why are large members weaker? It's not because there is something inherent to something being bigger that makes it weak. It has to do with the grading process. So for visually graded lumber like this, and like most of the lumber and larger single pieces of wood that you get, which are visually graded, they grade the piece of wood by looking at the outside, and they have kind of a checklist of all of the different criteria. How many knots are there? How many splits are there? Are there wanes? What is the grain angle on the piece of wood? Okay, that's visually graded. And that is since it's based on a visual inspection, it means you can only look at the sides of the piece of wood in order to figure out what the grade of that piece of wood is. If I have a small piece and I look at the sides, I can get a pretty good idea. Like I can get a pretty good idea looking at this piece that there's no knots hiding in here, right? Just by looking at the four sides, I can see there's not really any knots hiding in there. But if I have a large piece of wood, there's more chance that there are hidden defects on the inside that I can't see just by looking at the piece. So that's the primary effect that we're taking into account when we talk about size factor. So for the larger pieces of wood, to account for the fact that the grading process is less accurate because we're just looking at the outside of the piece, we reduce the strength. So you can see we have dimensions here, larger dimension and smaller dimensions. So for this piece, the larger dimension is this long dimension, which is 89. The smaller dimension is 38. So I would say, okay, I have 89 here. The smaller dimension is 38. So my bending and shear KZ factor, size effect factor, is 1.7. Okay, so it's 70%. Now these numbers are a bit arbitrary. They're based on a baseline. So it's basically, they did tests. The test value, the test pieces were this big, and then relative to that, they said, okay, what's the size of something that's this big? And they said, oh, it's 70% greater because the grading is better. So therefore, the factor is 1.7. So this is a function of where the strengths in the other tables are defined for. So, like if I went to the strength tables, the baseline size for that strength is a certain size. And then relative to that, the strength can either go up and down depending on the size. Okay, so going forward, we're going to talk about grading, and we're going to talk about how to actually find these strengths.